Hello, good morning. Welcome back to Short Lectures in Physics. The topic for discussion in this session is scattering of light. Light from sun has to travel through different layers of atmosphere. In the process, they encounter numerous air particles, water droplets, etc. present in the atmosphere. As they pass through the atmosphere, the light rays deviate from their respective direction of travel, and that is known as the scattering of light as they interact with the different particles present in the atmosphere. Due to scattering, light can be seen everywhere during the daytime. That means it gets scattered and enter into our rooms or any shaded areas so that we will be comfortable in seeing the objects even inside the rooms and under the shadow places. In the absence of atmosphere with such tiny particles present in it, it may be difficult to see the objects in such places. It has been demonstrated that a scattering of light takes place when the size of the scattering particle is very small as compared to the wavelength of light rays, because the wavelength of light rays is around start from 4000 visible range. So the particle should be less than 2000, around 2000 angstrom units or 0.2 nanometers. In this slide, you can see that the light from sun passes through the atmosphere, and while doing so, they encounter various particles of different sizes, and they undergo scattering process. According to Rayleigh's law of scattering, the intensity of scattered light is inversely proportional to 4th power of wavelength of the light ray. In IS, intensity of scattered beam directly proportional to 1 by lambda to the power of 4, or inversely proportional to 4 lambda 4. Lambda is the wavelength of the light beam that is undergoing scattering. The Rayleigh's law becomes invalid in case of light interacting with the large sized particles as compared to the wavelength of the light rays. Such particles are dust particles and water droplets of larger sizes. In such situations, all colors get scattered equally and making the clouds appear white or grey in the dark. Wavelength of blue color is about 4500 angstroms, while the for red it is about 7000 angstroms. As the wavelength of blue color is small as compared to red, more scattering is possible for blue color light because IS is inversely proportional to lambda. For lambda being small for blue, it gets scattered more. Thus, majority of the blue color reaches the earth, making the sky appear blue with silver-lined clouds during the daytime. Clouds contain large-sized dust particles and water molecules that makes all colors of light scatter equally and later merge together, resulting in white color. Thus, clouds appear white in daytime, and if it is dark atmosphere, then they appear gray. In this slide, you can see the various colors seen in the sky during the daytime. So, the intensity of scattered light is inversely proportional to 4 of the wavelength of the light. During sunrise sunset times, the sun happens to be at the horizon and hence has to travel through a larger distances as compared to the distances when the sun is directly above the surface of the observation during the noon time. So the light with the longer wavelengths like red, orange or yellow colors can only travel through such larger distances as light with the shorter wavelengths like green, blue, violet gets more scattered. Hence, such colors with shorter wavelengths cannot reach the earth. Thus, the sky looks in the less scattered red color during the sunrise or sunset times. In this slide, you can see sunrise or sunset times how the sky looks. It is reddish or yellowish reddish. As Red color is less scattered as compared to blue color. It is used as a stop signal in traffic control system. Even in foggy conditions, this red color danger signal can be seen by drivers and pedestrians from a far away distances. Oceans looks blue because of a scattering of blue light, that is lower wavelength, by water molecules is very large. Hence, the oceans also appear in blue color water bodies. Roads and streets are sometimes illuminated with the yellow sodium light because wavelength of yellow color is more than that for green and hence experiences less scattering and visible to illuminate the roads with sufficient brightness and with less air strain. Suppose assume that there is no atmosphere on the earth or the place of observation, then the sky appears dark and all stars can be seen even during daytime. This is because there will be no scattering of light from the sun due to atmosphere. During or after the rain, it is common to see concentric arcs of colors in the sky when the clouds are observed by a person standing, the sun having at his back. This is called a rainbow as arcs appear as bows. Formation of rainbow is due to shining of sunlight on the rain water droplets. It forms due to combined effects of refraction, dispersion, and total internal reflection phenomenon of light. Sometimes two types of rainbows are seen, namely primary rainbow, that is inner and brighter one, and secondary rainbow, outer and fainter one. In this slide, we can see the sunlight falling on water droplets after the rainy time and undergoing multiple processes of light. The water droplets are spherical in shape. The formation of a primary rainbow is due to two refractions, one total internal reflection and one dispersion of white light taking place as the light travels through the spherical rainwater drops as shown in the figure. The white light from sun enters the water droplets at a different angles. As they meet the first air-water boundary surface, they undergo refraction for the first time, then travel at a different angle of refraction depending on the angle of view. As they meet the opposite surface of the water-air boundary surface within the sphere of the water droplets, they undergo total internal reflection depending on the angle of incidence whose value is more than the critical angle. So they undergo total internal reflection and travel in a different direction following the reflection principles to the water-air boundary surface on the other side as shown in the slide. When the white light ray meets the water droplet surface for the first time, simultaneously along with the refraction, it undergoes dispersion also in the water medium and splits into colors with different wavelengths. Red color deviates through less angle as compared to violet color as shown in the figure. So, to an observer, the red color is observed at the top of the rainbow as the light gets emerges out of the water droplets, while the violet color is seen at the lower portion of it. Arcs of different colors are thus obtained from various droplets available in atmosphere with the red color arc at the top and the violet color at the bottom. All the other colors also appear in between these two colors as a spectrum. This formation of arcs with the different colors in the sky when observed in the direction opposite to sun position is called rainbow. The semicircular shape of rainbow is due to hindrance of light coming from sun by the earth coming in between the sun and rainbow location. Otherwise, the rainbow appears in a circular shape. In secondary rainbow, the sequence of colors seen gets reversed as compared to primary rainbow. In other words, the red color will be seen at the bottom of the rainbow while violet color at the top of the rainbow. And the secondary rainbow is larger in size than the primary rainbow. In this, the light rays from sun will enter the water droplets at their bottom part, unlike the primary rainbow in which the light rays from sun enters from the top portion of the spherical water droplets. In this slide, you can see the rays from sunlight falls at the bottom part of the spherical water droplets and gets refracted from the first surface, and then they travel through the water droplets and undergo total internal reflections at the opposite sides of the water droplet. The first total internal reflected beam meets the other side of the water droplet and again undergoes total internal reflection, and finally the angle of incidence becomes smaller than the critical angle, and hence again it refracts and moves away from the normal at the opposite side of the total internal reflected point. Depending on the wavelength of the ray, the violet ray is seen at the top as the observer looks, and the red color seen at the bottom of the rainbow because of the configuration shown in the figure. Thus, the light coming from the sun undergoes first time a refraction and then followed by two in total internal reflections and then emerges out through refraction process. Thus, in this formation, the ray undergoes twice refraction, twice total internal reflection, one dispersion. As a result, the red color will be seen below and the violet color seen above the observer. As the light undergoes twice total internal reflections, more light gets absorbed in the medium due to reflection process, and hence it appears fainter as compared to primary rainbow. When a light beam enters a dark room through a small hole or window gaps, the light gets scattered by the dust particles in the medium of air inside the room and becomes visible as a ray of light. Its path can be seen as a white patch, and this is known as Tyndall effect and is due to scattering of light in the medium with the large sized dust particle. This you can see in movie theaters. Once the projector is on, then the light coming from the projector onto the screen can be seen as a patch of white light in the dark hall. This phenomenon is also observed when light passes through tree branches at the sunrise or sunset times as streams of light rays coming from the branches. And this is also due to the Tyndall effect, that is scattering of light by large sized dusty particles. Unlike Rayleigh scattering, Tyndall effect can be observed when the size of the particles in the medium is roughly same as the wavelength of the light used. So this causes scattering of light number of times that they all merge together and appear as a white light again. The dispersion process is eliminated because of this. Tyndall effect is well known in identifying whether a given solution is of a colloidal or not. As light passes through a colloidal solution, the light gets scattered by the particles present in the solution, thus making the path of light being visible as it passes through the medium. The path of light beam cannot be seen in case the solution is pure and free from the colloidal particle. The intensity of scattered light depends on the concentration of the colloidal particles in the solution as well as the frequency of the light used. Blue light of smaller wavelength, higher frequency gets scattered more than the red light. Because of this, the smoke released by automobiles appear blue sometimes. This is some of the information about scattering of light and the various phenomena we observe in day-to-day life. I hope this gives you some insight into the scattering of light. See you in the next topic of lecture. Till then, bye.